at the end of that lecture, I'm going to tell you pretty much exactly what to study for the exam. Right, so, okay, let's, I guess we can begin now. So we're going to finish, at least to the extent that I'd like to, chapter 33 on, well, next Monday when, no, lecture, the exam covers only only chapter 30, up to chapter 31, including 31. Okay, nothing after chapter 31 is on the exam. So, we have demonstrated to some extent, the exam is the 16th, right? A week from Monday, a week from this coming Monday. So we kind of demonstrated that electromagnetic phenomena include the existence of electromagnetic waves, and therefore wave phenomena such as diffraction, reflection, refraction, and so forth are to be expected. So we're going to cover that, but I want to discuss a few more properties of electromagnetic waves before we launch into the actual study of optics. Right, optics is really kind of like applied electromagnetism because it's a natural consequence of Maxwell's equations, and then the wave equation and so forth. But first, I want to talk about the idea that light waves actually transport energy. Okay, just to give you an example, that you know, as I said last time, you just go out in the sun, right? You can feel the radiant energy of the sun from 93 million miles away. This is a slide that I actually use in my energy and environment class. So this is actually a great argument for solar energy, right? If we wanted to use, we know what the average insolation, the average solar energy input on the Earth is about. It's about 200 watts per square meter, right? That's this figure down here. And that's average over the geography of the United States, and over day and night, and over the seasons, right? It's an average value over the continental United States, I guess including Alaska as well. And if we wanted to generate all our energy, primary energy, with only about 10% efficiency of converting energy, solar energy to electricity, we could do it with this little 3 terawatt square over here. So the idea is that we could do it, but this is just an extreme application of the idea that that light carries energy, right? So the other thing I want to talk about is, let me do that. The other thing I want to talk about, concept I want to approach is the concept of polarization, right? Now, unfortunately, I have some really great demos that I would have used if we had had an in-person class, but the best I could do is just find some graphics. So we're going to talk about light waves, which have a variety of polarizations from, let's say, a standard source like a light bulb, for example. This is kind of, we tend to just write a random polarization as just a combination of 2 orthogonal polarizations. And the so-called picket fence analogy is that if you have this wavy string like a slinky, for example, and if the plane of oscillation corresponds to the slots, then then everything goes through. But if you rotate one of those picket fences, then you stop that, perpendicular to the plane of oscillation, then you basically kill it off. Okay, so that's so the way to do that with light is use a so-called Polaroid filter, right, where you get polarized light. If you've got kind of more high-end sunglasses that polarize, that basically only see the polarized light, then you cut a significant amount of energy out of that. There's some, later on in not today's lecture, we'll see that if you have unpolarized light reflecting off of let's say, glass or water, then you get partial polarization from reflection, right? Or if you have this calcite crystal and you have unpolarized light going through, you end up getting 2 refracted beams. The angle of refraction corresponds to orthogonal polarization. So you have 2 right angle polarized beams coming out, right? So we'll talk about polarization and about energy transmission as well. So let me for now move over to my tablet. Okay, so all right. So again, the first slide that I showed was meant to convey that that light waves, oops, that light waves. I'm having a little trouble with this. I thought this wrist pad was going to make it easier. Transport energy. Right. So we describe that with a vector. It's easy to remember what it's called. It's called a Poynting vector, but it's named after a scientist, Poynting, which is spelled this way, Poynting vector. And we use the symbol S, capital S. And S is given by 1 over the magnetic permeability times the electric field cross magnetic field, B, right? So that's going to describe the energy transport of a light, basically a beam of light, right? Notice the direction is defined by the cross product. And if you remember the graphic that I showed, or if you've read the book, that you have these oscillating electric and magnetic fields, E and B are mutually perpendicular, and then the direction of wave travel is perpendicular to both E and B, as described by the cross product, right? You know, so we had this E field, and we had a perpendicular B field, and both going in the direction, right? Described by the cross product. So the units of S are power divided by area. That corresponds to the insolation that I talked about, the solar energy, 200 watts per square meter averaged over the United States. So that would be in watts. That's watts per square meter. So the intensity, though, you step outside in a warm day and you feel the sunlight on you, you would call that intensity. The intensity is really just the time average of the Poynting vector, right? So average over time. Remember, you've got sinusoidal E and B fields, okay? So let's first get the magnitude. This is the time average, and we'll see how that goes in just a moment. Let's get the magnitude first. So S is equal to this magnitude, 1 over mu 0, E times B, right? We've already taken out the cross products. We already determined in the previous lecture, when we discussed the properties of the waves, that the B amplitude, the field, magnetic field, is the electric field amplitude divided by the speed of light. So therefore, S would be equal to 1 over C times mu 0 times E squared, right? So that's for an electromagnetic wave. How do we get the time average? This high intensity. The time average, which is represented by this S in brackets with the T subscript, time average would be simply, you take the constants out, 1 over C, mu 0, time average of E squared, right? So let's remember that we have a sinusoidal dependence of the electric field. That's 1 over C mu 0. We used for the amplitude of the field, we used E0 from last time. And then we take the time average of sine squared kx minus omega t. Okay, before I ask you, before you panic and say, well, how in the world do I do that? Let me just show you what a plot of sine squared looks like. Remember, the sine or cosine goes above and below the axis. The squared never goes below the axis, so the sine squared looks like this. So the average would be sort of like somewhere in between. Does anybody know what the average of sine squared of anything is over one cycle? Anybody have a guess? I'll give you a hint. The average of sine squared over a cycle is equal to the average of cosine squared over a cycle, right? And sine squared plus cosine squared equals what? 1. Okay, so what's the average of sine squared? 1/2. Thank you. Yes, good. I think you beat me to the answer. All right. Okay, so what we normally write is that the electric field, RMS, is short for root mean square, right? When you average root mean square, that means it's the square root of a half, okay, or 1/the square root of 2. ERMS would be equal to the full amplitude E0 divided by the square root of 2, and therefore I, intensity, which is time averaged, is 1 over C mu 0 E RMS squared. Okay, so let's talk about the energy density associated with the electric field and magnetic field. We already know when we talked about DC fields, we used the model of a capacitor for electric fields, a parallel plate capacitor, and for solenoid, for the magnetic field, we used the model of the solenoid. Okay, and we were able to show for those special cases that there was energy content associated with the square of those fields, right? And then I made the statement that this is general. It's independent of what form the field is in, what generates the actual field. And that's true as well for electromagnetism. So let's continue that argument. Let me clear the page here. And so what I want to talk about is energy density. In the E field. Right, so it's energy per unit volume. That's energy divided by volume. So if you recall from our previous discussion in chapter 25, the energy per volume of electric field, it was given by 1/2 epsilon 0 E squared, where E is electric field. For an EM wave, for an electromagnetic wave, that would be 1/2 epsilon 0. We also determined in the previous lecture that the amplitude E0 or E was equal to the speed of light times B. So this is from last lecture. So that would then be 1/2 epsilon, whoops. Let me clean that up a little bit. 1/2 epsilon 0, 1 over mu 0 epsilon 0 B squared, which is then B squared over 2 mu 0. So in chapter 28 or 29, I believe it was, we determine that that's the energy density of the magnetic field, so that the energy density, the energy carried by electromagnetic wave per unit volume is the same as the energy carried by the magnetic part of the electromagnetic wave. It's a very important result. It turns out that it's actually the electric field that we respond to in most cases. Like for example, if you're looking at a distant star, I'll do that example in just a moment. The part that actually stimulates your retina is the electric field in the electromagnetic wave emanating from the star. So if you have a point source, right? So let's say we have a point source, could be the sun or a star. Then the light goes out radially, so forth. And the wave fronts, these circles, these are the wave fronts essentially, and the perpendicular light rays would be these radial waves. These radial lines, but you have these, I can only draw this in 2 dimensions, so the circles. In 3 dimensions, there'd be spherical wave fronts going out. And the power, let's say the power of the source, let's say the PS is, let's say that's the total power emitted by the source. The intensity would be the power divided by the area of that sphere at that particular distance. Let's say some distance r. Then that would be, the area of that sphere would be 4 pi r squared. So you see that the intensity gets weaker and weaker as you go further out. It goes as 1 over r squared. It's sort of like the electric field due to a point charge. Okay, same geometric dependence. So I want to do, actually, I like this one. Sample problem, just numerically, 3301. This is page 982 to 983. Oops. All right. Any astronomers here? Yeah, I think there are a couple of people in the class that said they might be interested in astronomy. So this is a really nice example. Well, I want to figure out the magnitude of the electric field. If you look up on the sky and you look at the North Star. So here's the North Star, otherwise known as Polaris. Right? We know North Star is 431 light years away, right? And a light year is about 6 trillion miles. Okay, you can convert. You can look at the look up the numbers and all that stuff. And we also know that Polaris is pretty bright, right? It's 431 light years away. We also know from various other means that the total source of Polaris, very, very bright star, it's about 2.2 times, it's about 2,000 times the power due to the sun, okay? Very bright star, okay? Very big and very hot star. So it produces about 2,000 times the power of our own sun. We know that the sun intensity, this is a well-known number, is about 4 times 10 to the 26th watts. Not the intensity, the power. The sun puts out a total of, whoa, what happened to my 2? 4 times 10 to the 26 watts. So the intensity that Polaris puts out is going to be 2.2 times 10 to the 3 times 4 times 10 to the 26th over 4 pi r squared, where r is 431 light years. So you have to convert from light years to meters, right? We also know that then the intensity from our previous discussion, what we want to do is we want to get, I didn't tell you what we wanted to get. We wanted to get the electric field RMS and the magnetic field RMS at the Earth. In other words, an observer on the Earth, what electric field would they detect from the light coming from Polaris? So the intensity is ERMS squared, as we had last time, divided by C mu 0. And then we can flip that around and solve for ERMS. So ERMS would be equal to the power, this is the star Polaris, times C mu 0 over 4 pi r squared, all to the 1/2. All right. Let's see, I have a little bit of room left here. We can plug in those numbers. We get about 1.2 millivolts per meter. That's the electric field that that tickles the sensors in our retinas, right? Which is plenty. Yeah, it's a very small number, right? But it's enough to see. You can see Polaris with the naked eye easily enough, right? But that's the electric field. The magnetic field, so this is ERMS. BRMS is ERMS over C, speed of light. So that chops it down. And in units of magnetic field, it's very small. It's 4.1 picotesla. Pico is 10 to the minus 12, all right? It's a tiny, tiny magnetic field. It's not the magnetic field that stimulates your retina, it's the electric field. Okay, in fact, most detectors, astronomers charge coupled devices attached to their telescopes or other imaging media. In the old days, they used film, right? Photographic film. It's the electric field in the electromagnetic wave that actually does the chemical reactions of the film or sets the charges in motion, the charge coupled device that produces the image. Okay. Magnetic fields are also important, but not in observation of light. Okay, they're for example in magnetic resonance, right? It's the magnetic field part of the electromagnetic wave that actually does the work, but you have to have a special geometry for that. Don't think I'll be able to cover that in this class. Okay, so let's now move to polarization. I showed you some of those slides in the beginning. And I'm going to repeat a little bit of that pictorially. Oh, by the way, in chapter 33, I skipped the section on radiation pressure, which is kind of interesting. But some people think that if you want to explore the solar system with low-cost propulsion, you build a solar sail. Okay, you actually build this in space. You unfurl a very large reflective thin sheet, and the solar radiation bouncing off the sail can propel you very far for basically no energy cost. So that's kind of an interesting application. So let me now go to polarization. I'll clear the board here. This is mostly descriptive. There's not too much mathematics that I'm going to cover here. So for polarization, I would refer you to figure 30, I'm sorry. Figure 33.9 on page 986. Okay, now I'm only talking about the electric field E. Okay, so because it's kind of hard to include the magnetic field in this discussion because it's just the picture would be too busy. So let's say we have just two dimensions over here, x and y, or y and x here, and we have the magnetic field is perpendicular but not shown. Okay, I'm not showing that here. So if you draw just basically just one cycle of oscillation, like this, and you draw the electric field is going to be this vector. We just fill these in. I didn't mean to make these different amplitudes, they're the same. So this is the direction of wave travel, the direction of the Poynting vector S. And this would be an example of light that's plane polarized. What I mean is that the oscillation is occurring in just a single plane, the plane of my whiteboard, or the plane on your page, right? So if you look at this, if you're looking down the x-axis and looking at this head on, so in other words, let's say now we plant our eye over here. So that's our eye. We're looking down the x-axis. Then y is vertical and perpendicular to z. So we're looking down the x-axis. The electric field oscillation is along x, along y rather. Okay, we're looking at the x-axis. The electric field is going up and down. The oscillation direction is along y. So that's plane polarized. But in practice, for a non-coherent source like a light bulb, or for that matter, the sun, or or a match, or a flame, or whatever, normally you get all the planes of polarization represented. So your electric field, you're going to have all the things producing light. You're going to have this way polarization, that way, so forth. Many possibilities, and symbolically. There's no reason for us to represent all of them. Symbolically, we basically put that in compact form, and that is we just imagine that you have two perpendicular components this way. When you see this means it's unpolarized. Of course, you have, and any other component in this picture over here can be superposition can be resolved into two perpendicular components. So this is enough to describe an unpolarized light. So what if we have a polarizer? Now these, again, I had some really nice demos if I were going to do this class in person, which I have done, of course, in previous years. There's a really nice one with a board with a slot in it and a slinky. Slinky is one of my favorite demo devices, which anything with wave phenomena, a slinky is really great to show. But basically what that would be is suppose we have unpolarized light, so represented by just the two orthogonal polarizations. And you have the light beam going this way. If you pass them through a polarizer, just basically like a board with a slot, or actually a strip of Polaroid film, right, which has these organic molecules aligned in such a way that only the vertical oscillation is allowed. The horizontal oscillation is completely suppressed, absorbed. So what comes through is just the vertical polarization. The horizontal one gets absorbed. Okay, so that's how a polarizer works. So this is what's transmitted. What's transmitted is the polarized light. The horizontal component is absorbed. And in general, again, I was going to make this mostly descriptive and not too mathematical, is that the transmitted, which is polarized, intensity is going to be 1/2 the incident, which is unpolarized. If you have, or in general, let's say we have a, let's say we have polarization that's vertical, a polarizer that's vertical. And if the electric field oscillation makes an angle of theta with the direction of the polarizer, then if the incident intensity is polarized, the transmitted intensity would be the incident times the cosine squared of theta. Where theta is the angle between the electric field oscillation. So we have a polarized light coming in with the electric field. The electric field vector is polarized, but the angle of the electric field oscillation makes an angle of theta with this polarizer, which only permits vertical oscillation. You cut down the intensity, and you cut it down by a factor of cosine squared theta. Why is it cosine squared? Because remember that the electric field is cut down to e cosine theta, and the intensity is proportional to the square of the electric field. That's why you get the cosine squared theta. All right. And now I want to tell you something really interesting. This is actually, this particular description is not in the book, but I like it so much that I'm going to include it in my lecture. Remember that the basis of our discussion is that now that we know that electromagnetism predicts waves, right? Then we expect that electromagnetic phenomena are going to observe the laws of various wave phenomena that we've come to appreciate. So, for example, reflection, and refraction. So that's what I having some problems with my more than usual today, my coordination. Refraction. We'll talk about the laws of reflection and refraction. What I want to do is I want to show how this is related to a very, very general principle in physics that you'll learn later on if you stay in physics. And that's the principle of least action, which I will not, or in a special case that we're going to do here is the principle of least time. So this is actually a very famous French mathematician, physicist, Fermat's principle. Of least time. Okay, let's transform ourselves to a nice sunny beach, and this will be the shoreline. This is water. Here's the sand, and here's a poor, unfortunate, drowning swimmer. And here's an alert lifeguard. Okay, the lifeguard's got to get to the swimmer in the least amount of time, okay? But we know that if the sand isn't too hot or soft or whatever, we know that most people can run faster than they can swim, even a good swimmer, right? So the lifeguards have got to figure out what's the shortest amount of time I can get to this person, right? To save the drowning swimmer. So do I just run perpendicular to the shoreline and then swim a long distance here? No, that doesn't make sense. What if I just run over here and then if I run with swimmers and then make a mad dash? This is what's the least amount of time? Let's figure this out. Okay, so let's say that this distance is A. And this distance down here from the shoreline to the drowning swimmer, the vertical part, call that B. Right? So let's say I take a path that goes this way. Let me just draw a perpendicular over here just for reference, and then this way, okay? Now, I'm sorry, I didn't mean to do that. Let me erase that. I make the turn over here, okay? The angle changes over here. So the experienced lifeguard might, from many years of practice, might figure out exactly how far and what angle to run on the sand, and then to jump in the water and swim in a straight line this way, right? So we'll call this angle theta 1, and this angle theta 2, right? And this length is L1, and this total length, L1 is the total length that the lifeguard runs in the sand, and L2 is the total length that the lifeguard swims in the water, right? So which path is the least time? Let me make this figure a little bit easier to see. So this is kind of the path. This distance, that's the shoreline. This distance is A. And this distance down here, here's the lifeguard up top and the swimmer down here. This distance is B. So this is theta 2, and this is theta 1. And this distance, the total distance is D, okay? This total distance from here to here is D. So this is X. From here to here is X. And from here to here is D minus X. So what's the total time that it takes? The time that it takes, the time is the distance divided by the speed, but if we have two different paths, the total time, we'll call, again, this is L1, and this is L2. Just to remind you, the total time is going to be L1 divided by V plus divided by V1, right? V1 is the speed that you can run on sand, and then plus L2 divided by V2, where V2 is the speed that you can swim in the water. So let's define a new concept here, new quantity. We'll call this N, which is the ratio of some speed C divided by V. Okay, spoiler alert here. C is the speed of light, and N is called the index of refraction. Okay, we'll come back to that in a while, right? So, so this T then would be equal to N1 L1 plus N2 L2 over C. So let's just keep track of things. The geometric path length is just L1 plus L2, right? That's the total distance the lifeguard has to travel to get to the swimmer, right? But the optical path, the so-called, I'll put this in quotes because we're not doing optics just yet. We're almost there. The optical path length is, we have to take into account this different speeds. So we do that conveniently by N1 L1 plus N2 L2, right? So we want to minimize L optical, right? What does that mean? What does it usually mean when you want to minimize something? What do you have to do mathematically? Usually. What do you do when you need to find a minimum? I know you guys are thrilled with this analogy. You have to take a derivative instead of equal to 0. Thank you. So you have to do this. You have to do a dl. So, oh, by the way, this N1 L1 plus N2 L2 is L optical over C. We have to do a dl dt, I'm sorry, dl dx, because that tells us where we have to go make the turn. We have to do dl dx equals, whoops, equals 0. We have to solve that. All right, so give me a moment. I'll give you another moment to just, finish copying that down, because I need the whole board to do the next part, to take the derivative, set it equal to 0. All right, we're almost there. So let me clear this. So we want to minimize. First of all, we want to derivatize, take the derivative of this thing, which is n1. Now, I hope you have that in your diagram, because your previous diagram in your notes already, because for L, from Pythagorean, L is just square root of a squared plus x squared. That's L1. A squared plus x squared, square root. And then for the L2, we have n2 times L2 is b squared plus d minus x, quantity squared. So we want to take that derivative and set it equal to 0. Just lost my list pad. Not that it was doing me a lot of good. So let's go term by term. So the first one, we get n1 times, we pull out a factor of a half, and then we have a squared plus x squared to the minus 1/2. And we also pull out a factor of 2x in that derivative. So that takes care of the first term, plus n2. Again, we get a factor of 1/2, and then we have b squared plus d minus x, quantity squared. That's a plus sign there. Also to the minus 1/2. And we pull out a factor of 2 and a factor of d minus x. And finally, if it's a minus x, we also pull out a factor of minus 1. And we set that equal to 0. So that's the equation. I can make this more compact. So I can write this as n1 times x over square root of a squared plus x squared. Right, that's from the a squared plus x squared to the minus 1/2, is equal to n2 times d minus x over square root of b squared plus d minus x, quantity squared. Well, that looks pretty messy, but it isn't really, because if you remember your laws of trigonometry and the figure that I erased already, which hopefully is still in your notes, we recognize this term over here as the sine of theta 1, and this term over here is the sine of theta 2. Okay, so that gives us n1 sine, whoops, oh, I ruined my punchline by doing that. N1 sine theta 1 is equal to n2 sine theta 2. Anybody recognize that law? Let's give it a name. Anybody remember this from high school physics? Not Lenz. Snell, yes, thank you. This is Snell's law. All right. So what have I just shown here? What I've just shown is that light is smarter than even the most experienced lifeguard. I mean, an experienced lifeguard is going to get this pretty close to right, but a light ray has to get from point A to point B, or in the least amount of time. It always does that. It always knows, physics always knows that light travels along a direction in which it gets from one point to the other in the shortest amount of time. So the light's going to bend in just a way, and it's going to refract into the more dense medium, the water, just so that the angle of refraction is going to be given by Snell's law, right? So Anyway, I thought that was kind of neat. That's why I used the lifeguard analogy. Let's see if this principle of least time also works for reflection. Okay, of course the answer is yes, but we'll just go through the algebra if you don't mind. We'll go through that and then we'll take a break after that. So let me clear this. So here's reflection now. Oops, I lost my screen. So let me put down here an object which I'll call M, which is a mirror. And I have a light, let's say a light ray over here coming from point A, capital A. And it's going to go this way. Let's say this distance over here. Oh, this distance over here is little a. Okay, and it's going to reflect to some point over here, which we'll call capital B. So this distance is A, and this distance is B, little b, vertical distance. This angle is theta 1, which makes this angle also theta 1. This angle is theta 2, which also makes this angle theta 2. You thought that stuff they taught you in high school, you could forget about it, right? You can't, right? And this, we'll do the same trick we did before. We'll call the total distance between big A and big B. The total horizontal distance will be little d. So this is x. Ooh, what happened?
Welcome back. How's the thing?
this tablet I got is driving me nuts. Okay, so this distance is x, and this distance is d minus x. Okay. So here, the one important distinction here that, as opposed to from the case of refraction, is that in this case, the optical path length is actually equal to the geometric path length, right? Because we're only talking about this side of the upper side of the mirror, right? Okay, the light, whatever. Let's say this is air. This is having air. We're not talking about what happens behind the mirror. The light's traveling in the same medium, right? So we don't have to use an index of refraction. The optical path length actually is geometric path length, and so we have if you're in the same medium, then you only have a single speed to worry about, the speed of light in that particular medium. Okay, so the geometric path length is square root of a squared plus x squared. Sorry about that. Plus square root of b squared plus d minus x quantity squared, right? And then we take that derivative and set it equal to 0, dl dx. X is the variable of the variable here, and set it equal to 0. So we get 1/2, very similar to what we did last time, 1/2 a squared plus x squared to the negative 1/2, and we pull out a factor of 2x, plus 1/2 b squared plus d minus x quantity squared, again to the minus 1/2, and then we pull out a factor of 2 and a d minus x and a minus 1, just as we had last time. So we get, from that, we simplify, we get x over square root of a squared minus x squared is equal to d minus x over square root of b squared plus quantity d minus x squared. Right. again, if you look at the picture in terms of the angles, which what gives us that, what this tells us is that sine theta 1 is equal to sine theta 2. In words, or actually, even better, theta 1 equals theta 2. In words, the angle of reflection is equal to the angle of incidence. So we use what's referred to variational principles simply as to show just, when you likes to travel, will always travel in a minimum amount of time between 2 points. We derive Snell's law and we derive the angle of incidence equals angle of reflection law. Okay, so I'll put a little box around that. And so back to Snell's law, let's just say that, so back to Snell, we can express, another way to express equivalently, Snell's law is sine theta 2 is equal to n1 over n2 sine theta 1. So if the velocity in the medium is always less than the speed of light, okay? If it's air, it's only a little bit less, but so that means that n of all media is always greater than 1. Okay, so let me just read you. This is from page 992, table 33.1. So I encourage you to look at that, but I'll read a few of the values. So for example, in vacuum, right, you don't have any medium at all. In a vacuum, the index of diffraction is exactly 1, right? In air, it's a tiny bit bigger than 1 because air is, very sparse. You have few, you only have a certain number of molecules per, per volume. So it's an air would be 1.000, 3 zeros and then 3 or 29, 1.00029. Water, it's 4/3, 1.33, right? Acetone, it's a little bigger, 1.36. In fused quartz, it's almost it's 1.46. Let me go all the way to the bottom. The densest medium in index of refraction is diamond, 2.4, 2.42. Okay, so that's very interesting. That's one of the reasons. That's one of the ways that a jeweler can tell a diamond from a fake, like a cubic zircon. Okay, and that's why diamonds look so brilliant under light, right? Because as we'll see in, when we have to break, we'll talk about something called dispersion, where the index of diffraction actually depends on the wavelength. So a diamond disperses light very nicely and looks so colorful. So in the meantime, let's take a 10-minute break and I'll see you back in a short time. If there are any questions, you can post them up and I'll try to get to them when we come back from break. Okay. Okay, we're back. So I want to discuss refraction, right now that we have a kind of a firm grip on Snell's law, at least where it came from, and discuss a few cases, typical cases. What happened to my, here we go. So normally what we do is we have an interface between two media, and we specify the indices of refraction, N1, let's say above, and N2 below. And we always specify a perpendicular direction to the interface. That perpendicular is called the normal. I could just write normally, it would be better. So that's this is the normal. And we have a light ray coming in at some angle θ1. It gets refracted at the interface and travels this way with this angle θ2 inside, where here in this particular case, for N2 bigger than N1, then the refracted ray bends toward normal, right? So that means that θ2 is smaller than θ1. Okay, suppose we do it the other way around. Let's say, for example, the medium above was here, N1 was air, and the medium below was water. Suppose we do it the other way around, where, just as an example, this would be water, and this would be air above. Well, the index of refraction of air is approximately 1. You know, it's only in the 4th decimal place that you actually see a non-zero. Now let's do it this way. Let's now have where here we have N1 is bigger than N2. So we have N1 above, and here's our normal. So now we have a light ray coming in here with angle of incidence θ1. And if N2 is bigger than N1, I'm sorry, if N1 is bigger than N2, then it bends away. So this would be θ2. So in this case, the refracted ray bends away from the normal. Furthermore, N itself, the index of refraction is a somewhat more complicated entity than we may have thought in the beginning. It turns out that N in particular, didn't mean to put a subscript there, but the index of refraction of any medium essentially is really a function of the wavelength. So if you have white light, for example, and if you look carefully, you'll find that the refraction will actually disperse the light, such as what happens in a prism. I mean, actually, I'll refer you to the prism picture on page 994. I won't draw it, but classic. I mean, this is what Newton discovered, and it turns out that, for example, if you look at the wavelength dependence, index of refraction for blue light is bigger than the index of refraction for red light. So a blue light beam is going to be bent more than a red light beam. So, and this of course leads directly to the concept of dispersion, which is how a prism works. So even without doing the geometry of the prism, let's say we have on the upper side, we have air, on the lower side, we have glass. And we have, let's say we take a light beam, which is a mixture of two colors, let's say blue plus red. Well, the blue beam, what would happen is that the light, this blue plus red will split up into blue and red. I can do better than that. Might as well use the meager tools that I have. All right, so so you actually split the light beam up into colors, and a prism does that really well with white light, which is actually a spectrum of colors, not just blue and red. So, and by the way, this is all entirely predictable from Maxwell's equations. From the Maxwell's theory of electromagnetism includes the fact that the index of diffraction is going to be frequency or wavelength dependent. Okay, so it's all quite beautifully consistent. All right, let's do some general cases here and see there's a couple examples I want to show that actually illustrate the phenomenon of refraction. So I want to start with two refracting media. And I'm not going to show the, by the way, whenever you have this, you're also going to get some reflection. Okay, whenever you have light incident when light changes from one medium into another, travels into another medium, you get refraction, but you always get some reflection. Okay, but in the case I'm going to show now is I'm not going to actually show the reflected rays here, just to show you do get some reflection. But now I want to take two media. We'll call this, let's say we have a block of glass. We'll call that A. And we have another block of glass. We'll call that B. And they're different. They're made up, like one is flint glass and one is crown glass. They have different index of diffraction. So I want to shine a light ray in over here. So here's the normal. So this would be theta 1. So I have a light ray going in over here. It's going to be refracted. This is theta 2. Well, I'll call this theta A. Sorry about that. I'm sure you can't read that. This angle is theta A, and it's going to emerge with this. In fact, let me not make this theta 1. Let me make this theta I for incidence. This is the incident angle. The incident angle. The refracted angle is theta A. Okay, and it's going to emerge with the same. It's going to go. We go from the rare medium to the dense medium. It gets bent toward the normal, and we leave the dense medium, go back into the rare medium, and we should get the same incident angle, right? Actually, I just call that theta I. Now we enter the second one. Oh, didn't mean to do that. So now we enter the second medium. Okay, and it's going to get refracted with an angle theta B. And it's going to emerge. Everywhere we have an interface, we have to draw a normal. It's going to emerge at the original incident angle, theta I. Okay, so it comes out with the original incident angle out of medium A. So it enters with that incident angle in medium B, gets refracted to angle theta B, and emerges at the final interface between B and you know, the, let's say, air with the initial angle of incidence. So let's say this is let's say this is air or vacuum. Same thing out here. So let's do an experiment. Let's push these two blocks together. So this is A and this is B. So now I come in with my light ray. Here's my normal. This is theta I, and I get refracted theta A, and I get further, since B is different than A. Let's say B is even denser. I get further refracted theta B, but then I come out with the original angle of incidence that I came in. Okay, now we're going back to air. So what do we conclude from this? So the first thing we conclude is the theta, that the angles that we get is independent of separation between the blocks A and B. Second thing is that when you're all done, when you finally get out of all that stuff, there's actually no net change in direction. The third one, which is not obvious, but suppose I turned it around. You could actually do it, we won't do it, but we do it in our heads. Suppose I turned it around. Suppose I shine the light the other way around, instead of from left to right, from right to left, is that you would find this operation to be entirely reversible. You get the same angles. All right, I want to do an example which is not in your text. It might be one of the problems that I did not assign. But anyway, I'll do it. It's kind of neat because it's a familiar example. Let me clear this board. Before I clear the board, let me just describe the example. Things in water, things at the bottom of a pond, look closer than they actually are. Okay, or if you prefer a more local example, if you can't get to a nearby pond, take a coin and drop it in a glass of water, and you'll see, you'll have the sense that the coin is not as deep as it looks, closer to the surface than it actually is. So we can do that example in detail, which is what I want to do now. So this is I'll call this the apparent depth of, let's say, a coin at the bottom of a 1 meter pond. Water is one meter deep. So let's just say that has a preamble. The index of refraction of air, we'll call it 1. It's close enough. We don't need to go into the fourth decimal place. And that we're going to describe the angle. We'll call that sine theta A. And that's going to be by Snell's law. Oops, sorry about that. That's by Snell's law. Sine theta A, since n is equal to 1, is equal to n over water times sine theta water. Okay, and that's going to be equal to 1.33. So anyway, so this is 1.33. So what does that look like? Let's see if I can copy this properly from my notes. So up top we have air, down below we have water. And the coin is sitting over here, but the apparent image of the coin is somewhere up here. Okay, so this is the light reflected off the coin goes this way. It gets bent away from the normal. So this angle is theta A. This is theta air. This is theta water. And here's our viewer, right? Okay, but what the viewer sees is actually this, okay? Right, the viewer thinks that the coin is a little bit higher. So let's just put some dimensions into this. We'll call this X, and we'll call this, let's see, we'll call the real depth D. We'll call the apparent depth capital D, right? So, so by Pythagorean theorem, this line over here is x squared plus little d squared, 1/2. And the line up here, the other one is x squared plus big D squared to the 1/2. And so we get, whoa, lost my screen here. So we get sine theta, oops. So sine theta water is equal to x over x squared plus little d squared to the 1/2. And sine theta air is equal to x over x squared plus big D squared to the 1/2. Well, we also have, we know that by Snell's law, we have to plug back in the index of refraction. So NW times the sine of the angle, which is, I'm going to write as x as a head just above, x squared plus little d squared to the 1/2 is equal to x times x squared plus big D squared to the 1/2. So let's simplify that a little bit. So we square both sides. So NW squared times x squared plus big D squared is equal to just x squared plus little d squared. Let's make it a little simpler. Let's take the vertical view. If we now look straight down, vertical view would mean x equals 0. That simplifies things enormously. And what we get is NW times big D is equal to little d. So big D is equal to little d over NW. So if NW is 4/3 or 1.33, then that means if little d is 1 meter, big D is going to be 3/4 or 0.75 meters. So the coin is going to look closer than it actually is. There are other ways to do this problem. This is just one of the ways that I decided to do it. Okay, and I didn't look carefully, but I'm sure you're going to find something like that in the back of the chapter, chapter 33. All right, let me tell you about something really interesting that has a lot of great applications, and that's called total internal reflection. Okay, before I clear this board, since some of you might still be writing, can anybody give me an example of where total internal reflection is used in technology? Anybody? Well, okay, if you can't, I'm going to give you a couple of great examples. All right, so let me clear the board here. But first, I need to tell you what total internal reflection is. Um, so, well, sorry. Data transmission, yes. Fiber optics, okay, we'll get to that in a moment. Total internal reflection. And it goes like this. So now we're in the dense medium and we're shining a flashlight out of the water. Let's say this point P over here. So let's say this is water down below and air up above. So there are a number of things that can happen. Suppose I shine it, suppose I'm looking at a light ray that goes this way. So we'll call this, I'm going to turn it around this way. I'm going to call this theta 2. And you're going to have refraction away from the normal, right? We'll call this theta 1, because you're going into the less dense medium. All right, now I take this light ray over here, where this is theta 2 prime, and you're going to have theta 1 prime over here. Let's do one more. If you keep doing this, so this is theta 2 double prime. Eventually, theta 1, this is theta 1 prime, theta 1 double prime is going to be equal to 90 degrees. It keeps bending away from normal until it's actually right along the surface of the water, all right? Let's keep going, okay? So we have theta 2 triple prime. There's nowhere to go. I mean, you can't go more than 90 degrees, right? So all of course, you're always going to get some reflection over here, but you'll get transmission too. You can once you've surpassed 90 degrees, you can't get any more transmission, right? That's called total internal reflection, right? So if when theta 1 prime, well, triple prime, theta 1, let's see, double prime is equal to 90 degrees. Then theta 2 is called the critical angle. Actually, I don't need the primes anymore here. So when the angle of refraction is 90 degrees, that's when the angle of incidence is called the critical angle. Right? Here we have, of course, remember that this top is N1, bottom is N2, where of course N2 is bigger than N1. So what is the critical angle for total internal reflection? And that is, it occurs at 90 degrees. So sine theta 2 is equal to 1. So sine theta critical is equal to N1 over N2. Or we'll call that theta sub c, the critical angle, is the inverse sine of N1 over N2. I think the book has it reversed, or I have it reversed, but in terms of N1 and N2. But here, N1 is, for this is true for N1 less than N2. Okay, so let's look at a couple of cases numerically. So let's say we have glass and air. For glass, N is 1.5. For air, it's approximately 1.0. So for the glass-air interface, 1.5 would be silica glass, right? Basically window glass. Sine theta C is 1 over 1.5, or 0.67. And the critical angle then would be the inverse of that, 42 degrees. Okay, let me tell you now, you already, one of you, Tehan already told us about the fiber optics. I'll mention that in a moment. Let me tell you another interesting application. I'll clear this if you don't mind. Anybody ever used binoculars? Yes or no? Has anybody ever looked at it? Yes, okay. Let me ask you a somewhat more detailed question. Did anybody ever smash a pair of binoculars and see what's inside? Maybe not, all right? Okay, but if you were to do that, so let's just tell you what this is. You would find a pair of these, 45, 45, 90 prism. Multiple lenses of differing thickness. That's not where I was going. But it turns out that in order to get the effect of enlarging an image like you do in a telescope, now telescopes are long, so you can have your lenses, your objective and your collecting lens far apart. You can't do that in binoculars. So you have to increase the optical path length somehow. And the way that's done is by putting a pair of these for each eye inside. This is a right circular prism, 45 degrees. So light comes in, and because 45 degrees is bigger than the critical angle, which is 42 degrees, then you get total internal reflection, right? And out this way. So this is a way of increasing the path length in a limited space. So there's no transmission out here, okay, or here. So in order, we haven't talked, I don't know that we're going to get to talk about telescopes in this class, but there's a relationship between the two lenses, the distance between the two lenses. It's not big enough in a short set of binoculars, so you have to increase that by this trick of increasing the length, the path length. So the 45 degrees is greater than the critical angle. So the other one that Tehan mentioned is an optical fiber. Which is central to our industry of telecommunications and many others, data transmission. The way it works is it's basically, some people call this I'll put in quotes, a light pipe. It keeps the light inside, so the light, if you take a particular, let's say beam of light represented by these rays, every time you hit an interface, you get reflection. And because of the nature of the material, the fiber material itself, and the outside, which is called the cladding, because of the index of refraction of the transmitting medium over here, the light never gets out. Everywhere you hit an interface, you get total internal reflection. You don't lose anything coming out. That's why these fibers can be miles long, right? And without, you lose some, there's some things that happen. There's scattering and there's absorption and other things like that, but you don't lose anything. You don't get any of the light transmitted out of the fiber. gets total internal reflection. It's very important, probably the most important application of total internal reflection. I have some great demos that I would have brought to class if we had an in-person class of this, including fibers and lasers and stuff like that. But I apologize, I can't do that. Let me just mention that we can do. I also have a demo that I would have done with an ordinary glass of water called frustrated total internal reflection. It goes like this. Let's say I have two prisms, like two triangular blocks of glasses like that, like we have in the binocular prism, and I have another one like this. In other words, suppose I have a rectangular block like that, but I split it up down the diagonal, right? So if I have light coming in over here, right, it gets total internal reflected, right? It doesn't come out over here, and it doesn't get through. In other words, it doesn't get through. But what happens if I push these two together? If I push these two together so that they touch, then you just have an ordinary block of glass, and they're really squeezed together very tightly. It goes all the way through. So if we actually eliminate this different index of refraction which exists between them, and we push it together, obviously you would have no problem with transmission. Well, this leads to an interesting idea. Well, what actually happens at the surface? And electromagnetic theory, interestingly enough, shows that at the very surface, you still have some you still got some electric field going on. It's very weak. It decays very rapidly into the medium, let's say this is air in between, and that's called an evanescent wave. Okay, you could detect that, right? If you have very sensitive detection, the main way to detect it is to keep pushing these blocks closer and closer together until you get, you actually jump the gap if the gap is small enough, like, you know, a few microns or something like that. And then that proves that there was something in that gap, right? That's called an evanescent wave. The mathematics is actually quite fascinating. I can't go through it now for you. I'll just go through it descriptively. You'll have to take Physics 342, optics, which I believe is being taught next semester. And then the mathematics is actually fairly straightforward, okay? But I'll describe how it goes. What you get in here, in the evanescent wave, is you have some kind of imaginary component, e to the ix, right? Which is by Euler's form. You don't have, this is totally optional. You don't have to write this down. Just pay attention and absorb the beauty of this cosine x plus I sine x. So whenever you see e to the ix, that's a sinusoid, essentially. We know from Maxwell's, we know from what we developed already up to now, is that the light wave, the electric field, has a sinusoidal dependence, right? Well, what happens is that if you have, let's say, e to the ix and then e to the iy, but remember that I squared is -1, so that gives you an e to the minus xy. So it turns out the light wave has an imaginary component inside. Inside this medium where you go from, let's say, glass to air. Right at the surface, it's got this imaginary component, decays very rapidly because you have a decaying exponential, right? And you can catch it. You can actually detect. You can detect that, but the easiest way, as I said, conceptually, is you push another prism close together and you close the gap, or you could take a very sensitive detector and bring it really close, or even take a sharp knife edge, right? Right. This is normally total internal reflection. If you stick a very sharp blade, reflecting blade, right next to the surface, you'll get some reflection. Okay, so that evanescent wave is real. It decays very rapidly once you get to the less dense medium, right? But it's there, and that's called frustrated total internal reflection. Last thing I want to do today, I'll just set it up for you and we'll finish it on Monday. And this is actually not in the book, but I think it's important enough. And that's called absorption. So let's say we have some medium in here. We have light coming in, and we have a little bit less light coming out, right? Because some of it was absorbed. Excuse me. So I will call that the intensity. Same thing, same usage as before. And what we're interested in is that the amount of intensity inside here, di, in a very small segment of that medium, the amount of intensity that you have, basically, if you have absorption, the light intensity is going to increase as you go through the medium. The small amount of increase inside, first of all, it has to be proportional to I, right? Obviously, whatever that decreased di is going to be, it would be bigger if you also increased the initial intensity. So di is proportional to I, right? That's so. The constant of proportionality, we'll call that minus alpha. Minus sign means that as you go into the medium, of course, the intensity is decreasing. And it's also proportional to the thickness of the medium, which is dx. So we're talking about a very small amount of material differential quantity, right? So there is our basic differential equation, right? So di over I is equal to minus alpha dx. Integrate both sides, right? We've done this already. We've done this mathematically already several times. So natural log of I is equal to minus alpha x plus some integration constant k. How do we get that integration constant? We need an initial condition, which is that I is equal to the initial intensity that you had at x equals 0. So this direction, of course, is x. At x equals 0, you don't have any, this is the original intensity. So we plug that into into this equation over here, and we get, we equate this constant of e to the k as I0. So I then, intensity as a function of x is going to be e to the minus alpha x times e to the k, or I0 e to the minus alpha x. This is a very famous law. It's called Lambert's law. And this is actually very important in fiber optic transmission, okay, because the silica fibers are not perfect lossless transmission media. You get, there's impurities, and there's you actually shake the silicon oxygen bonds a little bit. That generates a tiny bit of heat. But when you're talking about kilometers of transmission, you get these losses, and that's why this is an important example. You also get, it turns out that this absorption coefficient, alpha, okay, so alpha is the absorption coefficient. And it turns out that alpha in most media is also a function of the wavelength or the frequency. So you get preferential absorption. Some colors are absorbed more than others. Last thing I want to say. Hey, does anybody know why the sky is blue? It's a little bit related to this. Why is the sky blue? Yeah, well, red light gets not filtered out, but yes, it gets scattered out. Yes, so let's let me come to that. So you can have absorption. You can also have scattering. Sorry. So you have light coming in, and you have this medium, and the light gets scattered by small particles. For example, molecules of nitrogen and oxygen in the air, or particulate matter like smoke and so forth. And then you have, when you've gone through a certain amount of medium, you get less coming out. So you also have a form of Lambert's law where I is equal to I0 e to the minus alpha with a subscript s times x, where this is not due to absorption, but due to scattering. Absorption generates heat. Scattering just sends the light in different directions. And alpha s, the scattering cross-section, or rather the scattering coefficient, is proportional to lambda to the minus 4. This is developed by Lord Rayleigh, and that's called Rayleigh scattering. So that means that things of the size of, it's mostly nitrogen, right? But nitrogen and oxygen, the molecules are small enough so that the blue light, what's coming out of the sun is white, essentially, has a spectrum. And the blue light gets, so we have sunlight. And the scattering preferentially perpendicular is blue. Okay, so that's why the sky looks blue. And when the sun sets, right, so this is the Earth, and here's the sun on the horizon, sunlight. You're scattering through much thicker atmosphere. All the blue light is gone. All the blue light has been scattered perpendicular out, and what's left is white minus blue or red. That's why the sunset looks red and orange. Okay, so if you happen to be in a polluted city, or if you have a lot of water vapor in the atmosphere, then all the light gets scattered equally, right? You have a very broad distribution of light, so the sky looks white or gray. Okay, if you have a lot of particles in the atmosphere. So anyway, we're done. I'll see you on Monday. Again, if you're going to miss a class, don't miss Monday's class, because I'm going to tell you what's going to be on the exam for the following Monday. So I will see you next Monday.